Looks like the upper questions for sure. All right, let's take a look at number 6 first. Says the car's wheels have a radius of 0.5 meters. The car travels at a speed of 15. What's the period of rotation of the wheels? The period of rotation of the wheels, capital T, right? Big T. We're going to say for this one, number 6, V is equal to 2 pi r over big T. And we're going to rearrange that to solve for big T. It becomes 2 pi r over V. We know what r is, 0.5 meters, and we know what v is, it's 15 meters per second. So 2 times pi times 5 divided by 15 should give me the period of time for one revolution. Does that make sense? Now, some of you may have been trying to use a is equal to v squared over r, or f is equal to mv squared over r. Are those valid equations for this problem? Sure they are. And we've got an object moving in a circle. Anytime you have an object moving in a circle, there is a centripetal acceleration and a centripetal force. We're allowed to try those equations. You're not going to get the wrong answer with those equations. Don't be afraid to try something. Okay, if this doesn't jump out at you, try something. Just try something that's valid, like a is equal to v squared over r, or f is equal to mv squared over r. If it doesn't work for you, then try something else. But don't be afraid to try it in the first place. Okay, next question was number 9. Number 11 says, what's the min speed of toy car, race car must move successfully through a vertical loop that has a diameter of 30 centimeters. So it's going like this. If it's going to fall out, if we're talking about a minimum speed, it's going to be at the top, right? You don't have to ever worry about the toy car falling off the loop here. Okay? If it's going to fall out, it's going to fall out at the top. At the top of the loop, there are two forces acting on this car. Gravity acts down, and what other force acts? Normal force, and which way does it act? Good. The normal force acts down. Which one's bigger? We're not sure yet. We'll figure that out. Next step, always the same when you have a free body diagram. The net force is the sum of the forces. This time the net force is mv squared over r. It's m times a, but specifically it's m times the centripetal a, which is v squared over r. Do we set Fn equal to 0? Only when you're looking for the min speed. Are we looking for the minimum speed here? Yes. So yeah, in this case, the normal force is 0. When you're looking for the minimum speed, the track doesn't have to help gravity push down. Gravity does the job on its own. Now, if you're not looking for the min speed, then you can't just cross off the normal force. It's there. Cross off the m's, appears in both terms. Looking for v. It's the square root of g times r. The r goes up by multiplying, and we square root that. So it's going to be the square root of 9.81 times the radius of 0.30 meters. Okay, whatever we end up getting there. It's pretty straightforward at this point. Yep. You're right, that's the diameter. So what do we got to do with that then, Austin? Good, got it in half. So it's going to be 0.15 meters. Thank you. Good? Okay. Oh, 12, yes, that's a good question. Somebody asked me about that before class. That's a great question. How many people got that question? Just a couple, eh? That's a hard question. At least it seems it when you're trying to do it on your own. The centripetal acceleration acting on a person standing at the equator. Here's the acceleration. It's v squared over r. But we don't know what v is. Well, we know that v is 2 pi r over t. We don't know what t is. Or do we? If I'm standing at one spot on the equator, how long does it take me to go around with the Earth and back to where I started? 1 day, which is 24 hours, which is a year. Oh, my goodness. You get the right idea, though, at least. You get the right idea. It's just wrong number. What is that in seconds? 86,400 seconds, not 86,600. So we're going to say 2 times pi times Tara, do you have the number for the speed there? Does that surprise you? How fast you're moving if you're standing at the equator? In a sense, it surprises me. I know, I've gone through enough problems in physics that I know you're moving really fast at the surface, on the surface of the Earth at all times, including at the equator. But still, when I see that number, it still surprises me a little bit. You're traveling about 1.5 times the speed of sound. You're traveling at Mach 1.3, Mach 1.4, as you're standing at the equator. Is that really the case? Well, sure it is. Why don't you feel it? Why don't you notice it? Yeah. How fast is the Earth moving at that point? Same speed. As long as you're moving with the Earth, it doesn't really matter how fast you're moving, right? You ever notice in an airplane that's traveling at 800 kilometers per hour, you stand up, you walk to the bathroom, you don't really notice it's going at 800 kilometers per hour? Because so are you. As long as you're moving at the same speed, it doesn't really matter. All right, what's the acceleration here? 463.96 squared divided by r is 6.38 times 10 to the 6. And what do we get for that one? .0337 meters per second squared. Make sense? So basically what we're saying here is this. If gravity couldn't supply an acceleration of 0.0337, what would happen to you? If gravity couldn't provide that much acceleration, what would happen to you? You would fly off the Earth, right? You would fly off the Earth. That's the amount of centripetal acceleration that's required to keep you moving in a circle on the Earth. Well, gravity supplies an acceleration of 9.81, so there's no issue whatsoever. You think you're going that fast? Oh, I'm going to fly off the Earth. Well, you would if gravity couldn't supply that centripetal acceleration, but clearly it does, and much, much more. You don't even feel like you're being lifted off because gravity is so much greater. All right, guys, finally, number 13 says an ant climbs onto the side of a bicycle tire at a distance of 0.4 meters from the hub. A 0.01 gram ant, I don't like grams, I want to convert that to kilograms, can hold onto the tire with that force. What frequency would the tire fling on ant off, assuming the wheel is spun at a horizontal plane? Well, the centripetal force is mv squared over r. Let's get v. The r goes up by multiplying, the m goes down by dividing, and then we square root that. R is 0.4 divided by the mass. 0.01 converted to kilograms. I'm just going to say 0.01 times 10 to the minus 3, right? Because that's what a kilogram is, right? 10 to the minus 3 grams. Or 1 gram, I should say, is 10 to the minus 3 kilograms. If you want to just move the decimal place, that's okay too. 17.36 meters per second. Now you want to find the frequency. Okay, solve for the period using the numbers you have, and then solve for the frequency using 1 over the period. Okay, the math should be pretty easy there once we get to this point. Okay? Are those all okay? Going to have ourselves a quiz tomorrow, everyone, on vertical circular motion. Okay, so let's make sure that we're okay with the whole normal force, the force of gravity, the centripetal force, and so on. Minimum speed, and so on. Vertical circular motion. Okay, quiz tomorrow. Yesterday we looked at the development of the current model of the universe and where it came from. We talked first about Aristotle and Ptolemy a couple thousand years ago, and we said that Aristotle and Ptolemy both had this idea that the Earth was the center of the universe, this far-fetched idea that the Earth is the center of the universe. But we talked about it not being so far-fetched a couple thousand years ago. We said the only reason that we, most of us, or all of us probably in this class, know that the Earth revolves around the sun versus the other way around is not because we look up and we can tell that by ourselves, but because somebody's told us. When we were in elementary school, we learned that the Earth revolves around the sun, not the sun revolving around the Earth. So it's not so far-fetched, actually, to think that the sun revolves around the Earth, the whole heliocentric model. We're wrong. Okay, we know that the geocentric model isn't correct. We know that the sun doesn't revolve around the Earth. Rather, the Earth revolves around the sun. But we didn't really know that. Nobody really knew that until 1,500 years later. Only about 500 years ago now, 450, 500 years ago. Copernicus, the heliocentric theory. The Earth and all the planets revolve around the sun, as opposed to the geocentric. The sun and all other planets revolve around the Earth. Now, Copernicus didn't say anything about that path other than that the Earth revolves around the sun in a circular path. Didn't describe it, didn't say why it does, didn't say how it does. It just does. The Earth goes around the sun. So a couple guys come along in the late 1500s, about 50 years after Copernicus. Tycho Brahe and his assistant, Johann Kepler. Tycho Brahe, he's the pee guy. He's the guy who went to the dinner party and held his pee and ended up dying because he wouldn't go pee. Tycho Brahe, and along with his assistant, Johann Kepler, made observations of the sky, the planets, the stars. They took measurements. They took angles and distances and times and all kinds of different measurements. Tycho Brahe didn't live long enough to do anything with that data. Johann Kepler, his assistant, did. Johann Kepler formulated 3 laws that describe the motion of the planets. The first law we call the law of elliptical orbits. It says that the sun is the center of the solar system, and all the planets in the solar system revolve around the sun in an elliptical path. Now you can see the Earth revolving around the sun here in an elliptical path. That ellipse is exaggerated. It doesn't really happen to that degree. It's much, much closer to a circle. But if I drew it to the degree where it actually happens, then you might not be able to distinguish the diagram on the board from a circle. Okay, it's very, very close to a circle, but it's not a circle. It's slightly elliptical. Now, the Earth revolves around the sun in the elliptical path. The ellipse has 2 focal points, 2 points. The sun is at one of those focal points. It's kind of a which came first, the chicken or the egg thing. Did the sun decide where it was going to be, and then the Earth decides where it's going to revolve around the sun? Or did the Earth revolve, and then the sun move to where it had to be in order for the orbit to be correct? The sun is where it is. The sun is either here or here. It's one of those 2 places. The Earth and all other planets form their revolution, form their orbit around the sun such that that position where the sun already is one of the focal points of that ellipse. Now, the Earth's orbit might look like this. Okay, Mars's orbit. That's not a good diagram. That's close to the center. Mars's orbit might look something like this. Okay, and then it goes on past the border there. Does that make sense? So for the Earth, the sun is at one of the focal points. Since the orbit of Mars keeps going way over here, then the focal point for Mars is at the right focal point, right? The sun is at the right focal point. Okay, it's okay. The sun has to be at one of the 2 focal points for every planet. In the elliptical path, one of the 2 focal points for every planet. Then we talked a lot about the equal areas, the law of equal areas. This is a tricky one. In words, this one says, a line joining the Earth to the sun. Here's the sun, here's the Earth. A line joining the Earth to the sun sweeps out equal areas in equal times. So in other words, if we look at the area in here between these two red lines, and we look at the area in here between these two red lines, those two areas will be the same. If the two times are the same, if T1 equals T2. Now, what are the implications for that? Well, it tells us that the Earth has to change speed as it goes around the sun. Think about it. If it's going around here, it covers a really, really big distance in that amount of time. In the same amount of time over here, it covers a much smaller distance. So it's going faster over here than it is over here. As the Earth goes around the sun, it speeds up when it approaches the sun. And then when it gets slingshotted around the sun, then it slows down again. Yep. Right. The question, if you didn't hear it, guys, was how we're going so fast relative to the rest of the solar system and the rest of the universe. What would happen if something mysteriously made us stop on a dime? I mean, that's a pretty hypothetical question, right? Because there's nothing that can really make it happen instantly like that. But let's say, hypothetically, it did. Let's say, hypothetically, we'd stop. What would happen to us? Well, I don't know how fast the Earth is revolving around the sun. Actually, I'm not sure what that speed is. So I can't comment on that one. But if you talk about the Earth's rotation and the Earth's rotation stopping, would you fly off? No, because gravity is more than sufficient to apply enough centripetal force to hold you against the Earth, right? Now, as the Earth orbits around the sun, there's a centripetal force caused by not the rotation of the Earth on its axis, but the revolution of the Earth around the sun. I'm not sure what that centripetal force is. My guess is it's probably still sufficient. Well, I guess if it stops, there's no centripetal force then anymore, is there? Okay, so I guess if it stops, I guess you fly off, wouldn't you? Because there's nothing to pull you back in. Yeah. So, sorry, Liam. Seemed like good news at the beginning would be okay, but if the Earth was to suddenly stop, we'd fly off into space. Sorry. That's what would happen. Okay? How many people have seen the movie Apollo 13? It's an old movie, so a lot of people your age haven't seen it. The movie Apollo 13 is based on a true story. The idea is that it was one of the lunar missions that the Americans had. I believe it was in the early 1970s to go to the moon. The first lunar landing, I believe, was Apollo 11, and landed on the moon July 20th, 1969. And then the Americans sent up kind of a few spacecraft after that to land men on the moon. Well, this Apollo 13 developed a problem, and I can't remember what the issue was, but the problem was such that it couldn't land, because if it landed, they'd never be able to get back. So what do? Well, they have to come back, right? They have to come back to Earth. But the problem is they don't have enough fuel to just turn on a dime and come back to Earth, because they don't pack enough fuel for that, right? They don't intend on ever having to, here's the moon, here's the Earth over here. They don't intend on ever having to just, oops, let's turn around and go back. They're traveling through space on the way to the moon with very little fuel, because they're coasting through space. They don't need very much fuel on board at that point. So how do they turn around and get back? Yeah, they use the gravitational pull of the moon. So this Apollo spacecraft, instead of turning around right here and going back to Earth, which the intuitive thing would be to do that, right? Turn around and go back. What they do instead is keep going. They keep going. And then they go around the moon. What happens? As they go around the moon, what happens to them? They gain speed. They speed up. Let's slingshot back here. And now which way are we going? Back towards the Earth. And we use very little fuel in that process. We use the moon's gravitational pull to slingshot us back. I'm sorry? Wasn't it a little risky? It was not a little risky. It was very risky. But it was the best option they had, because there was no chance of them getting back if they just turned around and tried to come back. Very risky. Now, there was a whole lot of things in that movie. That was a great movie in terms of entertainment, but it was also a great movie in terms of physics as well. They talked a couple of times about a couple of different things that put them off course of where they expected to be at a certain point. They're on their way back. Okay, it's all good. They're on their way back. Oops, they're not where they expected to be. They're close, but they're not where they expected to be. They had to be not close. They had to be exactly where they wanted to be. Otherwise, what's going to happen when they reach the atmosphere? If they hit the atmosphere at the wrong angle, what's going to happen? They might skip right off the atmosphere. It's like skipping rocks off of the surface of the water. They skip right off and then they're gone. They're off into space, and that's where they're going to die. So they have to hit it at just the right angle. If they hit it at a different angle, then they're going to burn up as they come in, right? So it's critical that they get it perfect. What put them off? A couple of things put them off. One, what do you think they do in space? I mean, you guys have seen videos of all this stuff on YouTube when Chris Hadfield was in space, right? Videos of how they do this, how they brush their teeth, how do they go to the bathroom in space. What do you think they do ultimately with the waste? They throw it out. It goes off into space. The moisture usually gets sucked out of it, and then they use it as drinking water. They filter it and use it as drinking water. And then the solids get Throw it out into space. What happens if you throw something out that way? If you apply a force on something out that way, it applies a force on you that way. So that puts them off course a little bit. The other thing is, such a silly little thing that they almost overlooked. As they're coming back, they're off course a little bit. Why? Because their mass is off by a little bit. Why is their mass off by a little bit? Pardon me? Because somebody lied about their weight? Yeah. Because they plan to land on the moon. And when they were going to land on the moon, what were they going to do? They're going to pick up rocks. They're going to bring moon rocks back. So they didn't land on the moon. They were coming back. They were a little light, lighter than they expected. And nobody anticipated that because everybody anticipated them having moon rocks on the spacecraft as they went back. They fixed it, and I won't tell you how it ended. But it wasn't a... Go ahead. William, I'm not sure if, to be honest, when they slingshot around the moon, I don't remember for sure, but I think what they would have probably done is, as they slingshot around, given themselves a little bit of speed, given themselves a little bit of a boost to basically take them out of that orbit. I think. I can't really remember exactly for sure what they did, but it's a good movie. You guys should watch it. I watched Gravity here a couple weeks ago. How many people have seen Gravity? How many people liked Gravity? I thought it was pretty good. Apollo 13 was infinitely better than Gravity was. Like way, way better than Gravity was. Way better. Okay, this is new. We didn't do this one yesterday. The third of Kepler's three laws, the law of periods. The law of periods says that the square of the period of revolution of an object going around the sun, or the moon going around the earth, or something revolving around something else, the square of the period of revolution divided by the cube of the radius of revolution is equal to k, a constant. And we call that constant Kepler's constant. Now, I'm not going to write down a number for Kepler's constant because it's not constant for every different object. If we're talking about the Earth going around the sun, and we use data for the Earth for the period and the radius of revolution, then we're going to get a certain number for Kepler's constant for the sun. If we use data for Mars going around the sun, different period, different radius, then it'll be the same value for Kepler's constant because the object being orbited, the sun, is the same object. If Neptune is going around the sun and we use the period and the radius of Neptune going around the sun, then Kepler's constant for the sun will still be the same. But if we're talking about, say, the Earth as being the object that's being orbited, the moon is orbiting the Earth, a comet is orbiting the Earth, the space station is orbiting the Earth. All three of those things would produce a number, Kepler's constant for the Earth, that was the same, but different than Kepler's constant for the sun. Does that make sense? So if we say t squared over r cubed for the Earth, we're going to get Kepler's constant for the sun. If we say t squared over r cubed for, let's say, Neptune, we're going to get Kepler's constant for the sun. And Kepler's constant for the sun is the same value always. But if we say t squared over r cubed for the moon, we're going to get Kepler's constant for the Earth because it's orbiting around the Earth. If we say t squared over r cubed for the space station, we're once again going to get Kepler's constant for the Earth. These two numbers are the same. These two numbers are the same, but these aren't. So what difference does that make? How does that help us out? How does that give us something that we need to know? Well, this is actually what allows us to find data about other planets. If we know what t squared over r cubed is for the Earth, then that gives us Kepler's constant for the sun. Well, now we have Kepler's constant for the sun. If we know what the time of revolution for Neptune is around the sun, then we can calculate the radius of revolution because we know two of the three variables. So it allows us, given information about one planet, to deduce information about another planet. Does that make sense? The good news is we're not going to have to do any calculations with Kepler's law here. You're just going to have to know the idea that essentially data for one planet can get you information about another planet by deduction. Okay? All right. All this is well and fine. The Earth moves around the sun. It's an elliptical orbit. The law of equal areas, the law of periods, all this stuff about how the Earth orbits around the sun. But why does it orbit around the sun? Why? Why does it go in an elliptical path? Why does the law of equal areas hold? Why is it going around the sun versus the sun going around the Earth? Why does all this stuff happen? What's that mysterious connection between the Earth and the sun that makes this thing happen? Well, as the story goes, and I'm not sure if it's really true or not, Isaac Newton is sitting underneath a tree one day, and all of a sudden an apple falls on his head, and he has this epiphany. When the apple fell on his head, he somehow reasoned that that apple was being pulled down towards the earth because of the mass of the earth. In other words, Newton said that objects with mass will attract each other. The earth will attract the apple because the earth has mass and the apple has mass. When the apple falls toward the earth, it falls because of gravity. The earth has mass, the apple has mass. Gravity pulls those two objects together, just like gravity pulls the earth toward the sun. That's what keeps the earth in orbit around the sun, this mysterious force of gravity. Any two objects with mass will exert a gravitational force of attraction on each other. We just did a little demonstration where you looked at your neighbor and talked about the force of gravitational attraction between you and your neighbor. Why don't you feel that? You feel the force of gravity when you jump off of a desk, right? You feel gravity pulling you down. Why don't you feel your neighbor pulling you towards him? Okay, good. The force of gravity towards the earth is more powerful. Why? Why is the force of gravity acting on you towards the earth more than the force of gravity acting on you towards your partner that you just did that little activity with? Because the earth has more mass. Right? There is a force of gravity between a grain of sand and another grain of sand, but it's so ridiculously small, you're never going to measure it. You start talking about the mass of the earth, though, all of a sudden that force becomes pretty significant. Why? Not just the fact that the earth does stay in orbit around the sun in an elliptical path such that the law of periods holds and the law of equal areas holds, but rather why the earth stays in orbit around the sun. And for that matter, why the apple falls toward the earth when it falls off the tree. All right, Newton described an equation, or derived an equation that described the force of gravity between two objects of mass. And the equation was this: F is equal to G. It's a big G. It's a constant that you've never heard of until this point. Talk about what that number is in a second. M1 times M2. M1 is the mass of object 1 in kilograms, right? And force of gravity between you and your neighbor. M1 is the mass of you. M2 is the mass of your neighbor. The constant times M1 times M2 over R squared. R you'd think would be a radius, but it's not. R is just a distance of separation, a distance separating the masses. And that's going to be measured in meters. G is the really new thing here. That's called the gravitational constant. And its value, no matter where you are in the universe, is the same. 6.67 times 10 to the minus 11 Newton meter squared per kilograms squared. That number's on your data sheet, by the way. If you ever need to use that on a test, and you will, then look on your data sheet for 6.67 times 10 to the minus 11. Now, if you were to find the force of gravity between you and your neighbor, we could do that pretty quickly, right? We could say F is equal to 6.67 times 10 to the minus 11. Let's say your neighbor has a mass of 60 kilograms. You have a mass of 50 kilograms. Let's say you're a meter apart. What do we get there for the force of gravity between you and your neighbor? 2.0 times 10 to the minus 7 meters. Newtons, sorry. Why don't you feel it? How ridiculously small is that force of gravity? Even on ice, even with no friction, even in space, how much of a force is that really? Like nothing, really. It's immeasurable. But when you're talking about the force of gravity between, say, you and the Earth, we're talking about a different order of magnitude, right? A significantly bigger force. It's kind of a tough question to start off this unit with, or this section with. Page 206, it says Mount Logan in the Yukon is 5,959 meters above sea level. 6 kilometers above sea level. That's pretty high. It's the highest peak in Canada. Earth's mass is 5.97 times 10 to the 24 kilograms, and the radius is 6.38 times 10 to the 6. What's the difference in the weight? Weight is force of gravity, right? At the top of the mountain as compared to the bottom. Well, let's get the weight at the bottom. We got 6.67 times 10 to the minus 11 times 55 kilograms times 5.97 times 10 to the 24. Hey, what if I had to change the order of those? What if I had to make the Earth first and then you? Doesn't matter. What's 1 times 2? 2. What's 2 times 1? 2. Does it matter what order we multiply those numbers in? No. 55 times 5.97, 5.97 times 55 doesn't matter. At the bottom of the mountain, the Earth's radius is 6.38 times 10 to the 5, 10 to the 6 meters. Let's get that number for force now. We get 538.049 newtons. Let's get the force at the top. What would you expect the force to be at the top? Your weight, more or less, or the same? More? At the top of the mountain? Okay, let's figure out. It's almost the same question, right? Slightly different number on the bottom here, though. This time the radius isn't 6.38 times 10 to the 6. It's 6.38 times 10 to the 6 plus 5959. Because our distance now is from the top of the mountain to the center of the Earth as opposed to from the bottom of the mountain to the center of the Earth. So let's figure this one out. 6.67 times 10 to the minus 27, 10 to the minus 11, I should say, times 55 times 5.97 times 10 to the 24. Let's divide that by, let's do some brackets here, 6.38 times 10 to the 6 plus 5959. Square that. And we get 537.04. What causes the curvature of space-time here? It's the Earth, right? The further you get away from the Earth, we drew that diagram a little while ago when we were talking about that, right? Here's the Earth. The further you get away from the center of the Earth, the weaker that curvature is going to be, the weaker the pull of gravity is going to be. That's why when you're on the top of Mount Everest, you weigh about 1 Newton less than you do at sea level. You ever notice when you go to Vancouver, you weigh more? Of course you don't notice, because it's such a small amount, but it's measurable. Okay, it's a measurable amount. It's just a small amount that you're not going to notice, but it's measurable. Make sense? Okay, here's your homework. Page 207, question 1 and 2. Let's see what you can do with that, okay?